Welcome to Civil Engineering Edge, your go-to destination for mastering structural design concepts. In today's video, we dive deep into the design of slabs as per IS 456 to 2000, from basic introductions to one-way, two-way, continuous, flat, and circular slabs. Whether you're a civil engineering student, an industry professional, or simply curious about how buildings stand strong, this video is your perfect starting point. So grab your notes and let's begin the slab design journey. Simplified, practical, and aligned with IS standards. Design of slabs. Introduction as per IS code. Slabs are essential horizontal structural elements in any building system. They transfer loads primarily to supporting beams or walls and play a major role in shaping floors and roofs. According to IS 456 to 2000, slabs are classified based on support conditions and aspect ratio into one-way, two-way, continuous, flat, and circular slabs. The design of slabs involves consideration of loads dead, live, and superimposed, span-to depth ratios, deflection and cracking control, shear and moment distribution, minimum reinforcement percentages, cover requirements, and concrete grades are clearly defined in the IS code. Slabs are usually designed as flexural members, assuming the bending action governs their behavior. The design is based on limit state method, ensuring safety, durability, and serviceability throughout the structure's life. Understanding the classification and behavior of different slab types is the first step toward accurate and efficient structural design, especially for real-world applications. Design of one-way slabs. A one-way slab is a slab that bends in only one direction, typically when the longer span is more than twice the shorter span LXLE greater than 2. These slabs are supported on two opposite edges, and the load distribution is along the shorter direction. They behave like a series of parallel beams and are common in corridors, footpaths, and narrow rooms. As per IS 456 to 2000, the following steps are involved in the design. 1. Determine effective span smaller of clear span plus effective depth or center-to-center distance between supports. 2. Calculate design loads. Dead load plus live load plus finishes. 3. Assume effective depth D based on span-to-depth ratios. 4. Compute bending moment using standard formula. MWL to 8M equals a frac WA 8M equals 8WL to for simply supported slabs. 5. Calculate area of steel ast using M equals 0.87F, Y has TD1 ASTF, Y FCKBDM equals 0.8 underscore Saint D. 1. Fraca underscore street F underscore, YF underscore CKBDM equals 0. 87 Fiast 1 FCKBD ASTFY. 6. Check for shear strength, deflection, and provide proper anchorage. 7. Place main reinforcement along the shorter span and distribution steel in the longer direction. Minimum reinforcement must not be less than 0.1% of the gross cross-sectional area for FEF or 1.5 steel. Proper cover and bar spacing ensure durability and crack control. Design of two-way slabs. A two-way slab is used when the slab is supported on all four sides and the ratio of longer to shorter span is less than 2 LX. Li is less than or equal to 2. In such slabs, loads are distributed in both directions and bending occurs in two orthogonal directions. These are commonly seen in square or nearly square rooms. As per IS 456 to 2000, design is carried out using moment coefficients from an XD for different support conditions. Main reinforcement is provided in both directions. Edge conditions, such as fixed, simply supported, or free, impact the distribution of moments and reinforcement. The slab is divided into middle strips and edge strips, where moment concentration varies. Reinforcement is placed accordingly. Shear checks are essential near supports. Deflection control is done using span-to depth ratio, modified with stress and reinforcement factors. Proper corner reinforcement is also essential in slabs with restrained corners to avoid cracking. Design of continuous slabs. Continuous slabs span across multiple supports and are more efficient than simply supported slabs. They reduce bending moments due to moment redistribution and result in thinner slabs with reduced deflection. IS 456 to 2000 allows moment redistribution up to 30%, enabling more economical designs. The design involves calculating fixed end moments or using moment coefficients, designing for positive and negative moments at midspan and supports respectively. Anchorage and development length are crucial at supports to resist negative moments. Reinforcement is placed as bottom steel in mid-span regions for sagging moments, top steel over supports for hogging moments. The continuity leads to better load sharing and serviceability. Crack width control is also improved due to reduced moment values. These slabs are widely used in long corridors, commercial buildings, and parking structures where multiple bays are constructed in series. Design of flat slabs. Flat slabs are slabs directly supported by columns without using beams. They are ideal for open floor plans, parking structures, and high-rise buildings due to their architectural and construction advantages. Design as per IS 456 to 2000 Clause 31 includes division into column strips and middle strips, load distribution using direct design method DDM or equivalent frame method EFM, special consideration for punching shear around columns. Flat slabs must be checked for shear stress at critical perimeters, moment distribution in both directions, deflection and cracking control. To counterpunching shear, designers may use drop panels thicken slab portions, column capitals, shear reinforcement. The reinforcement layout in flat slabs is more complex due to bidirectional behavior. However, the absence of beams allows for quicker formwork and construction, as well as flexibility in space usage. Flat slabs offer both structural efficiency and aesthetic appeal. Design of circular slabs. Circular slabs are slabs with a circular plan, often seen in tanks, silos, fountains, and architectural domes. These slabs may be simply supported or fixed along the edges and are designed considering radial and circumferential bending. As per IS 456 to 2000 and Advanced Structural Theory, the load is assumed to act uniformly over the surface. Bending moments develop along radial MR and tangential MT directions. The design is based on elastic theory and plate bending solutions. Reinforcement is placed radially from center to periphery, tangentially in concentric rings. Critical points for maximum moments typically occur at the center and edges. Special attention is needed for edge detailing and support conditions. Although rarely used in common buildings, circular slabs are essential in hydraulic structures and special architectural forms. Proper reinforcement detailing ensures load distribution is smooth and aesthetically pleasing while maintaining structural integrity. And that's a wrap on the design of slabs as per IS 456 to 2000. From one-way and two-way to flat, continuous, and even circular slabs, you now have a strong foundation to tackle any slab design. If you found this video helpful, give it a thumbs up, share it with your fellow engineers, and don't forget to subscribe to Civil Engineering Edge for more structural insights. Drop your doubts or topic requests in the comments. And as always, keep building smart and strong.